Okay, folks, so you don't need to jot this down, but so far we've learned how to find the volume of this green shape right here. So you can see this green shape, it lies between the, I guess I didn't label these, this is the x-axis, this is the y-axis, and here we have our z-axis. So this green shape lies between the xy plane and the surface f of xy. Okay? And so we interpret the double integral as a way of computing this volume if f of xy is always greater than or equal to 0, or if it were sometimes above and below the x-axis, we would consider it as the net volume. So we've got this tool, and the thing I want to highlight is up to this point, all we've been able to do is if the region that we're dealing with is itself some sort of rectangle. And our strategy, as we'll develop in class, is to break this up into a bunch of little sub-rectangles, take a point from each sub-rectangle, plug it into the function, from there compute a little column, and add up the volumes of a bunch of little columns. And we're still going to do that, but and we'll still be able to do it the same way, but we're going to be a little bit more careful now, and we want to look at doing this for an arbitrary region. So I would pick up taking notes on this now. So the key thing is that for the double integrals that we've looked at, the region R was a rectangular region. That is, we were always dealing with something of this form for the double integrals or their equivalent iterated integrals that we've computed so far. But what if, say, we had this question right here where we've got, we want to compute the volume of this surface, and this surface is formed, in this case, by taking the parabolic cylinder and then intersecting it with a plane up to some x coordinate here. But the point is that if you look at where the corresponding, if you take all the points that would be in this solid shape, they would all have corresponding xy values coming from within this region R here. Well, this region R is not rectangular. It's not at all like this example here. So what are we going to do? Well, it turns out everything will work out okay in the end, and we will develop that in class. But we're going to start working with some general region R, and we're going to need to be very careful in our description of the region because we no longer have a nice rectangular region here. But at the end of the day, we will find that we're going to compute the double integral the same way. That is, we're still going to take some x star k, y star k, so that's, here's the kth, this is our kth rectangle right here. We're still going to take some point in it, plug it into the function that will help us compute the height of this column here, and we will do that for all of these other rectangles that we've constructed inside of our region R, and we'll have to learn how to deal with the boundary. We'll briefly talk about how to deal with that boundary. But essentially, that's going to give us the height of a column times the area of the column. That gives us the volume of a column. And then we're going to add up a bunch of volumes of columns, still just as we've done before. So anyway, what I'm saying here is we'll eventually learn how to do this for some general region. Okay? And we'll learn how to do this in class. But let's go ahead and actually practice doing this. So let's look at this example here. And in this example, we see that we no longer have a rectangular region in our domain space. So first of all, let's just draw that domain space a little more carefully. The first thing we'll do is, I'll just keep the orientation the same. Here's x, here's y. So just looking at the domain space, we've got this region right here. This is our R now, and R is no longer rectangular. I'm going to, just for the sake of my own ability to think about things, I'm going to go ahead and reorient it the way we normally, that's not how we normally orient it. Here's x, here's y. And so we could think of this space right here, the domain space, the domain region R, as it's being bounded by x equals 1 here, and here we've got the y equals 0 for this curve, x equals 1 for this curve, and then this is the curve y equals x. I'm using the word curve even though these are straight lines because this applies to curves as well, what we're about to do. Okay, after some practice, you guys will get good at drawing these regions R. So this is, let me shade that just softly here. There's our region R. Okay, just as before, that we want to find the volume of this. So in fact, we can go ahead and, we're ready to even say that, right? Our goal is to find the double integral over our region R of 2 minus y squared dA. Okay. The problem is and just like before, what we'd like to do is break this into an iterated integral. But the problem is here how we do that as an iterated integral. It involves a couple of choices. So the first thing I want to do is I want to say that, in our iterated integrals, again, what we think of is we're thinking of kind of slicing this plane up, slicing this region up into little planes that look like, they're sitting inside here. Here's the let's see here, in our YZ coordinate system. So here's the z-axis, here's the y-axis for that plane that I just drew. And so if you thought of our curve, it maybe looks something like that, right? That's a parabolic-shaped curve. As I slice it, that's the best I can do. I know this isn't a great picture, folks. But that's just one slice in here, and then I would scoot over, and I would take another slice, and I would do that for all x values between x equals 0 and x equals 1. So you don't have to worry about drawing a picture quite as messy as this, but what you do need to do, and this is where the skill for doing these iterated integrals comes into play, is you need to be able to draw, represent where those slices are coming from in your region here. So I'll try to always do that in red, and I'm drawing these red vertical rectangles here. That's as opposed to drawing red horizontal rectangles here. Okay. So let's just jump into it, and then in class we'll be a little bit more careful about how we do this. So what I'm now going to do is I'm going to say, well, okay, I'm going to choose to write this as an iterated integral, which I can by a variant of Fubini's theorem, and I'm going to add up these little planes, each one running from the plane. This was maybe this is the plane x equals a half, and maybe this is the plane x equals 3/4, right? These planes run from x equals 0 to x equals 1. And then each one of these planes, we find the area inside there by taking the integral of 2 minus y squared dy. But the thing is what am I going to use for my limits of integration? And that's what I want to highlight here. So notice that all of these rectangles always start off with a y value of 0, but they finish up with the y value of x. So I'm going to write y equals 0 to y equals x. And this is the key here, folks. This could have been any function, any f of x, any y equals f of x function here for that upper curve. And frankly, y equals f of x. And frankly, down below here, we could have had any, curve y equals g of x. And so what I'm doing here is I'm not putting a upper limit as a number here, but I'm putting it as a function. Here in this case, y is a function of x. That is the hardest part of this, and then everything else is just computing the iterated integrals as we've already learned to do. So let me just go ahead and finish this problem out. So this would be the integral from x equals 0 to x equals 1 of, and then if we integrate this with respect to y, first we get 2y minus minus 1/3 y cubed. 1/3 y cubed, and this is evaluated from y equals 0 to y equals x dx. And so if we go ahead and actually replace all of our x's or all of our y's with the upper limit of integration there, we would have 2x minus 1/3 x cubed. And then just to keep this kind of general, I'll keep writing 2 times 0 minus 1/3 times 0 cubed. And all of this is being integrated with respect to x now. And so we get x equals 0 to x equals 1. So notice that this second term contributes nothing. And so we just end up with 2x minus 1/3 x cubed. And this is what I'm going to integrate with respect to x. So doing so now gives us, well, let's see here. This would give us, we have to divide by 2. So this gives us x squared minus 1/12 x to the 4th, evaluated between x equals 0 and x equals 1. And so we get 1 squared minus 1/12 times 1 to the 4th for the upper, and then the bottom contributes nothing. And so we end up with 11/12 for the volume of this shape. This shape here, which, let me go ahead and clean up my drawing here now. You can see that's the volume of this shape here, which the author was able to sketch far better than I. So folks, that's the first issue that we want to look at. And so we'll go ahead and leave it there, and we'll jump into examining, breaking down what exactly we mean by these different curves for our limits of integration. As you see in this next page, we're going to learn how to treat each of these different cases. So that'll conclude this video, and we'll pick up on page 6 in the next video.